All right. Thanks everybody for coming. My name is Anton. I'm here to talk about the current state of row-level operations in Spark and also give you a preview of what's coming next. So I'm Iceberg PMC member and Spark contributor at Apple, where I work on cloud services. For the last 5 years or so, I've been working on internals of query engines, table and file formats, trying to make our data lakes a little bit more reliable and efficient at scale. A lot of the work is done in open source, so if you happen to have any interest in what I do, what my team does, and like what even better, you want to collaborate, let me know and we can chat after the session. That would be awesome. And like quick disclaimer, I'm sharing my personal views, not necessarily the views of my current employer or any of the projects that I'll be mentioning. The talk today will consist of 3 sections. I'll start by outlining big data use cases that require row-level changes. I will also cover challenges that data engineers used to face trying to perform those operations on top of data lakes, and what even forced them to move some of those workloads to data warehouses, and how things changed and evolved and where we are today. And specifically, we will talk about delete, update, and merge in Spark and how it's helpful. And at the end, I'll wrap up with a few key takeaways that I want everybody to remember. All right, let's talk a bit about row-level mutations and big data. There is a variety of use cases that require row-level changes, but most frequently I see the following 3 scenarios. First, teams have to remove records for regulatory compliance. And you're lucky if that somehow aligns with your partitioning spec, but in most cases it does not, which makes it a challenging problem at scale. Second, mistakes during ingestion are inevitable. Table formats like Delta and Iceberg, they try to prevent some of those by enforcing a schema, offering you data quality checks, everything that they can do, but this is still not enough to capture business logic bugs. And when mistakes happen, you don't want to start from scratch. You don't want to re-ingest everything, or even worse, look for a point in time when things started to fail. It's much easier to go ahead and fix the current state of your table using an update statement if that's possible. And third, very popular use case is you need to populate changes to your data lake from some external systems. And those updates are not only inserts, they can be deletes, they can be changed records as well. Like common examples are change data capture and some form of slowly changing dimensions. For years, data engineers working with data lakes were using the following approach to perform row-level changes. They would collect all of the changes in a data frame. They would query partitions of the table that they think can be affected, and they would join these 2 data frames, form some aggregations, maybe window functions, maybe call a few UDFs, in order to compute the new state of the partitions that they read. And then eventually they would write this data back, replacing the content of those partitions with a new state. While this kind of worked, and I'm sure like everyone who's here tried it, there were a lot of issues. First of all, it was unnecessarily complicated. It forced us to express sometimes fairly simple business logic in terms of joins and window functions. It doesn't have to be that hard. Also, it was easy to make a mistake or miss an edge case because the query was so complex. It was really hard to make sense of it when you just look at it. So it took you quite some time in order to find those edge cases and test it and so on. Another major issue was performance, because this approach is limited to rewriting entire partitions, even though if you want to modify maybe a couple of records or records in a couple of files. That's why your jobs were slow, and they required a lot of resources because you were shuffling a lot of data that you didn't change, but you had to keep in order to basically build a new state of your partitions. And as a consequence, a lot of engineers would basically quickly find themselves tuning shuffles, making sure your cluster is coping with the load, instead of focusing on the use case that they have at hand. Last but not least, this was not reliable. Specifically, users were responsible for some non-trivial validation, such as detecting ambiguous cases. Let me give you an example. So if the incoming relation with changes contains multiple updates for the same row in the target table, we don't know what the new state should be. The SQL standard, for example, requires us to throw an exception, and the whole process is called the cardinality check. But I've never seen that being implemented in user pipelines that replace partitions, just because it would add even more complexity and it would degrade the performance even further. So most of the people just gave up on that validation and assumed that the user knows what they are doing. Apart from that, there were no asset guarantees. So overwriting partitions is generally not safe. And as I said earlier, this process of computing the new state also takes time. And it's highly likely that there would be another process that would try to add data to the partitions we're about to replace. And if that happens, then you would silently corrupt the table and you would lose data. In order to kind of prevent that, a lot of people would introduce some external locking and force everybody to go through that lock to make sure that there is only one writer at a time. But that would be complicated and still very fragile to fail. In other words, if ease of use, performance, or correctness was a big concern for your row-level operations, then most likely you would consider something else. You would maybe consider a data warehouse, which in turn would lead to a more complicated data processing landscape, because now you would have the same data copied into multiple systems for different types of analysis, and then you will have a hard time trying to keep the data in sync and pristine. Luckily, things started to change with the rise of new table formats and changes in query engines that they triggered. Right now, users can leverage a declarative command like merge, and then the query engine would be responsible for rewriting that command and handling the validation that is required. On top of that, table formats now provide full asset compliance. And they also boost the performance of these operations using indexing. All in all, recent developments in data lake query engines and table formats finally unlocked efficient row-level operations on top of data lake, so you don't need a data warehouse anymore for this effort, which in turn led to simplified data processing landscapes and allowed organizations to save both time and resources. So we covered use cases, we covered challenges and how things evolved in the past. Now let's talk about Spark and what particular tools you have within Spark that can help you to perform your row-level changes. The first SQL command that Spark supports is called delete. It basically allows you to remove records in your table that match a condition, and that condition may or may not include a subquery. So in this statement, we have a predicate on the department column, and then we have a predicate subquery on the ID column. The next command is update. It's very similar to delete, but instead of removing records, it allows you to update them. And you have a set clause that defines how the new values should look like, essentially. The most powerful command, though, is merge. It allows you to insert, update, and delete records in a single operation. And hopefully, that will be an atomic operation if your data source supports this. In every merge statement you see, there will be an on condition, which also called the search condition. It defines how the incoming records match records in the target table. In this statement, we're saying that if records have the same value in the ID column, we consider them as matching. But you can have any logic that matches your use case. Following the on condition, you can have a number of when matched, when not matched clauses that define the behavior of your merge operation. So you can have as many as you want, but you need to provide at least one in order to trigger this operation. In this statement, we have we're saying that if there is a match for the incoming record and the value, the incoming value of the op column is called delete, then we would like to remove the record from the target table. If that's not true, but we still have a match, then we want to populate the new value of the count column and update the target table. And finally, if there is no match for the incoming record, we just want to add it to the table as is. So as you see, merge is very powerful. It allows you to do multiple things at a time, but it also comes with a cost. So there is cardinality check that's going on under the hood, and also the rows have to be merged. So if your use case could work with a delete operation or with an update operation, you should use that instead of merge. So the grammar for these commands appeared in Spark 3.0, but up until Spark 3.3, Spark could only resolve and parse these statements. It could not execute them. That's why table formats and data sources that support these operations, they would have to provide custom Spark SQL extensions. And if you're not familiar with Spark SQL extensions, it's essentially a mechanism within Spark that allows you to plug in external analyzer, optimizer, and planning rules at runtime. In practice, this means that there is a lot of low-level Spark code that lives outside of Spark, which you try to inject at runtime, and you hope that's going to work. As you can imagine, it's a nightmare to maintain. You never know when it breaks, and also it limits the integration you can have. It limits what you can do with these operations. And on top of that, it prohibits any collaboration between different communities behind various table formats, which is really unfortunate in my view. That's why there is an SPIP in Spark, which was submitted a year ago. The purpose is to support these operations natively within Spark. The proposal was submitted around a year ago. It has been discussed, voted on, and it's partially implemented. So you see parts of it already in Spark 3.3. The main idea of that proposal is that Spark should be the one responsible for rewriting your declarative commands like merge and executing the query, doing all the validation. And data sources should be able to just plan the job and also commit the changes that were computed by Spark. Data sources do not have to write Spark code in order to support these operations. And another major goal was to have an API that would work across data sources so that different communities can work together rather than having similar yet slightly different implementations in their own repos. And in order to come up with a common API, one needs to understand different ways to implement and to support row-level changes. And I think it would be fair to say that there are currently two ways data sources behave. Some data sources handle deltas of rows, and some data sources replace groups of data. And then a notion of a group can be something like really different. It can be a file, it can be a partition, or it can be part of the file if you have a custom file format and you can swap that. I'll have a couple of examples next so that we are on the same page with the differences between these approaches and what Spark needs to do in order to support them. As an example, I'll be using a simple delete statement that basically removes all the records where ID is equal to 1. And we'll assume that we have a data source that is capable of atomically replacing files. So Iceberg and Delta and Hootie would be good examples for that. So in this case, a group would be a file, but a group is anything like it's the smallest unit of data that you can atomically replace. In case of Hive tables, this would be a partition, right? But we'll assume that we have access to replacing files atomically and that we have a data file with 2 columns, department and ID. And there are 3 records with IDs from 1 to 3. So whenever we'd like to handle this delete operation, the real question is, what should Spark compute and pass back to the data source so that the data source can encode this operation? And as it turns out, if the data source replaces groups, then you need to pass a new state of that group. In our case, this would mean that you need to read the original file, you need to discard the records that match the condition, and then you need to pass the rest of that group to the data source, and then the data source would write this out and atomically swap the pointers. Fairly simple idea. It's like really close to what we used to do with replacing Hive partitions, but just the notion of a group is different. And it makes a big impact, right? It is important that we can swap smaller parts, but essentially that's the same algorithm we've been using for years. The primary benefits of these approaches are simplicity and no extra work on read. Most of the time, table formats would easily support these operations, and the new versions of groups will look exactly the same like the groups before. So if we're talking about files, then those files look exactly the same as the files produced by inserts. And the table format would normally have some sort of snapshot isolation so that you would know which files you need to read. It actually surprisingly works really well for targeted bulk updates. If you can narrow down the scope of this operation to a couple of partitions or a small subset of files, then this is going to perform really well. Also, if you're rewriting, let's say, 25 or 50% of records in a lot of files, then it's actually cheaper to materialize those updates right away rather than come up with something fancy and apply those changes while you read the table. At the same time, there are limitations, apparently. The primary limitation that all unmatched rows in the group that we modify, they have to be copied over, which increases write amplification. In the example we saw, we had to copy over 2 records even though we did not change them, right? And that makes this approach perform poorly when you're modifying a small number of records in a large number of groups. So suppose you have 1,000 of data files and then you need to change a single record in every data file. You have to rewrite all of those like 1,000 data files entirely. And that's going to be expensive. And if it's a write-heavy use case like this, then it's not going to perform well. An alternative approach is to handle deltas of rows. And what that means is that you would probably use some sort of a differential file and encode a change at the right time so that you can then apply it while you read the table. And when it comes to what Spark needs to compute, then in this case, for Spark, it is sufficient to compute the changes, right? And instruct the data source to apply those changes. So in this case, we just need to pass that the record with ID 1 in department HR has to be deleted, right? If you have a merge use case, there may be some records that you need to update or insert as well. But the main idea that instead of producing a new state of groups, you basically pass back whatever changed and whatever the operations you need to encode. The primary benefit of this approach that it reduces write amplification, because the number of changes that you pass and the number of changes that data source has to process is directly proportional to the number of records that you modify. So if we go back to the example when we have 1,000 of data files and we modify 1 record in each of those files, then Spark in this case would just pass you 1,000 records. It would not touch like all of those remaining records in those files, which is a big deal for write-heavy use cases. At the same time, there are some drawbacks. So you can say which of the approaches is better. They have different trade-offs, so they both make sense. But this approach, usually there is some extra work while you read the table. So you need to discard the records that were removed. And then it's up to the data source to handle that efficiently. And the performance will also highly depend on the number of deletes you need to apply. which means that you would need to do a little bit more table maintenance on your table. Because in case of Iceberg, this is implemented using delete files. So those delete files, they have to be compacted. You have to export them as well, just like you deal with data files. As it stands today, Spark 3.3 supports delete operations that replace groups of data. Technically, that means if you're interested, you can go ahead and try to support delete operations for regular Hive tables that would replace partitions. That's going to help you with ease of use, but it won't solve the correctness issues and the performance problems. But at least it won't be as hard as it was to use it. The current API is fairly simple. So we added the supports row-level operations interface that you need to mix in on the V2 table. So it's not something that's supported for data source V1. It's purely data source V2 concept. The primary goal of this interface is to provide a row-level operation builder. It's very similar to the builders we have for scans and writes. That builder will have access to user-provided options and the SQL command that's being executed. So we'll know whether it's a delete, update, or a merge statement. The builder itself is fairly simple at this point. In the future, we'll have some mix-in interface because some builders will support some optional functionality. So as it stands today, it just builds you and configures appropriate row-level operation given the provided options that you have. And the core proposal, and the core part of the proposal is the row-level operation object. So if you think of what happens under the hood, then we read the target table, we perform some computations, and then we write the changes back. So you need some sort of coordination between the scan and the write, and that's exactly the purpose of this interface. Data sources like Iceberg and Delta, they, for example, support different isolation levels for your row-level changes. And under particular isolation level, you need to validate that whatever you read is still there. And on top of that, that every concurrent operation that happened also does not conflict with what you're trying to do. And that's what this interface basically allows you to do. It gives you access to your scan in the write. And then basically your scan can report a list of groups that were replaced, and then you can use that information to commit the changes. While deletes for group-based data sources is already supported, there's still a lot of work ahead of us. Specifically, the work with updates and merge is still ongoing. It's covered by the design doc, so it's just a matter of implementing that. Another major effort that's currently in progress is runtime group filtering for data sources that replace groups of data. So this one is a tricky concept, but if you're familiar with how Delta and Iceberg work, and in this case, this will be the copy and write approach, whenever you submit an operation, there is a condition. And those tools will look for a condition that can be pushed down and evaluated using metadata. So if you have a predicate on the partition column, a predicate on the sort key, that information will be collected, and the metadata will be used to prune files. You will use your zone maps, you will use Bloom filters, whatever your metadata persists, and whatever you can leverage. But it's not something you can use all the time. If you have a predicate subquery, you cannot evaluate it against metadata. And on top of that, metadata can give you still false positives, because zone maps are still like an aggregated min-max values, and Bloom filters are not 100% precise sometimes. That's why there will be false positives. And because rewriting groups that don't have to be rewritten is extremely expensive, then both Iceberg and Delta, they submit a quick subquery to evaluate what are the files that have to be replaced. And then this basically guarantees that you replace the minimum set of files that you need to replace. And this is what I call the runtime group filtering. It is essential to those tools. It's not something that the data source V2 supports right now, but there is a PR for that. So it's coming next, and will be part of 3.4. And finally, support for data sources that can handle deltas of rows is still ongoing. So it's also part of the design doc, and if you're interested, just take a look, let us know what you think, and we'll be happy to discuss it. All right, a few key takeaways from this presentation. And the first key takeaway that I wanted to convey is data lakes can be as efficient and as reliable as data warehouses. There has been a tremendous amount of innovation in data lakes in the last years, and I think this trend will continue. And I think the focus will be on ease of use and performance. I think those are two aspects where we still have a lot to do, but I'm confident that that's possible. So there is nothing that would stop us to be as easy to use and as performant as data warehouses. The second point is that when you're performing row-level operations, then your query engine works together with the table format. So you have to pick both options wisely based on the set of requirements that you have. That's basically all I had. Final note, if you are into distributed systems and you like working on open source, we have a lot of open positions. So you can work on Airflow, Flink, Spark, Trino, and Iceberg. Thank you.
Thank you, Anton. We do have about 5-6 minutes for questions. So if you got one, raise your hand. I'll come around with the microphone. All right, here in the front.
Do you know the general support that you're expecting for Parquet?
Say again, sorry?
Do you know the general support that you're expecting for these operations for Parquet format specifically?
So as I said, so it's part of, like, the release are part of 3.3, so I expect the CPI to be fully done in 3.4 with all of the features that are basically required for performance, for validation, and everything. And I think would be really beneficial for data sources to switch it for two reasons. I think we will be able to provide superior performance for them because this will be native within Spark. And second, we will allow them to basically reduce a lot of maintenance, right? Because they would not have to do a lot of Spark development in their own repos. So hopefully that will be something that will be adopted quickly.
If I have like 1,000 delete statements, I'm going to get like 1,000 files, right? Mm-hmm. And if I get 1,000 files, is that going to cost like where I got to read all those when I want to do a select clause? Because the tiny file problems, when you're reading hundreds or thousands, is going to slow me down. Will that automatically compact at some point? Mm-hmm. So 1,000 tiny files will be just one, or?
Yeah. So that's a good question because, like, again, your row-level operation essentially means you read something, then you do some computation, then you write back. A lot of that time is spent you write back. That's why basically you want to have that as efficient as possible. And there are things that can be done at the query engine level, and there are things that can be done in the table format specifically. So compaction would be something that's part of the table format, and I think all of the tools provide your optimized statements that you can do bin packing, you can do sorting, you can do multidimensional clustering using z-ordering or like Hilbert curve, whatever your data source supports. But there are things that you can do at the query engine side. And if you're familiar with adaptive query execution, that's the one that's capable of coalescing two small tasks. And as of master right now, your merge operations will be able to support it. So if there is a shuffle and then like you have a lot of shuffle partitions and like technically you can write a lot of small files, but adaptive query execution should be able to coalesce them together. So my colleague from the Spark team actually implemented that recently. It's not part of Spark 3.3, but it's part of the master. So it should be there in Spark 3.4. That is a huge deal. So we've seen that be really important for our production workloads. Another major effort is that something that I did personally is that the data source can request the distribution on write. So it can request Spark to cluster the records by, let's say, partition columns before the data is written. So that's another step that we're making, but you have a lot of control and you can prevent the small file problem.
So you talked about there's benefits and drawbacks on both the replacement and the delta strategy. Is there any plan to allow the query optimizer to suggest a particular strategy to the data source based on cardinality, things like that?
That would be cool to support, but as it stands today, I think if we're talking about data sources that support these operations, I think you have Hudi, Delta Lake, and Iceberg. You have Hive Acid, but not really. So basically, like if we're talking about those three, then in case of Hudi, as far as I know, it's something that you define in table creation. So it's not like you can have different types of operations. Maybe I'm wrong, but you can do that in Iceberg, for example. So you can have multiple operations on top.
Yeah, but I mean, like for Delta would be a good example. Like it clearly supports row-level operations, but in a lot of situations, it probably would be better to just overwrite. Like if you're doing
I don't think Delta Lake supports deltas as such. So they still copy files under the hood. There are plans to do that, but it's not something that's available right now and never been available, neither in the runtime, Databricks runtime, nor in open source. That would be a cool feature. So I think we will need to propagate some sort of metrics from Spark as part of that row builder, so you can probably have some optional mix in and where Spark would provide some stats and then the data source would report basically back whatever the approach it needs to do. Because there will be a switch in the analyzer. The row level object that the data source would build would say which approach to take. So basically that's definitely possible. It's just a matter of propagating those stats from Spark.
One more question over here.
Going back to Parquet files, since we usually do an overwrite, what's the main difference between using the delete function here to just, let's say, query the data source and then filter out whatever you were planning to delete?
I think the problem here, so if I got the question correctly, so what would be the difference from trying to, I'm not sure I really follow.
You ran an example saying we want to delete wherever the ID is 1. What would be the difference today when we're doing just filter out where ID equals 1 and rewriting the data set to doing a delete here that also does a rewrite of the data set?
Yeah, I think essentially it's what copy and write does, right? But you need to do that atomically. You need to do it efficiently so that you you do this quickly and it's reliable. You don't see any partial results and everything. So you need to have a data source that would support these operations. It's not something that a Hive table supports. So if you swap a file, that's not atomic, right? And in order to find out which files you need to change, that's also kind of sometimes really slow. So the other table formats have more functionality like indexing that can boost the performance of those operations. So essentially you can't do this because at the end of the day, that's what happens. You find out what files you need to rewrite, you rewrite those files, and then you commit the changes. But you need to have those properties and those qualities to make it reliable and usable in production, basically.
All right, that's all the time we have today. Can everyone just thank Anton again for his great talk?
Thank you, folks.